Ground rods serve a vital role in electrical safety by providing a path for fault current to return to the source, tripping a breaker or fuse and preventing electrical shock. While it is permissible to install ground rods inside a basement, it is generally not recommended and considered a less optimal solution compared to outdoor placement. The primary reason for this preference lies in soil conditions. Outdoor soil tends to retain moisture more consistently than the soil directly beneath a basement slab. Moisture content significantly impacts soil resistivity, which is the measure of how well the soil conducts electricity. High moisture content translates to lower resistivity, making it easier for electrical current to flow. When a fault occurs, a lower resistance path to ground allows the fault current to quickly reach the overcurrent protection device, causing it to trip and energize the circuit. If ground rods are installed inside a basement, the drier soil conditions may result in higher soil resistivity. This increased resistance can impede the flow of fault current, potentially delaying the tripping of the breaker or fuse. In such scenarios, the risk of electrical shock or fire hazards could be elevated. The National Electrical Code, or NEC, provides guidelines for grounding electrode systems. While it permits indoor ground rod installation, it emphasizes the importance of achieving a low-resistance ground. Section 250.56 of the NEC addresses grounding electrode system resistance. It states that if a single grounding electrode has a resistance to earth of more than 25 ohms, it must be augmented by an additional electrode. This requirement highlights the code's emphasis on ensuring effective grounding, regardless of the electrode's location. When considering ground rod placement, several factors should be taken into account. Firstly, the soil type plays a crucial role. Sandy soil generally has higher resistivity compared to clay soil. Secondly, the depth of the ground rods is important. Deeper rods typically encounter more consistent moisture levels. Thirdly, the proximity to other underground utilities must be considered to avoid accidental damage during installation. The NEC specifies requirements for the size and material of ground rods. Typically, ground rods are made of copper-clad steel or stainless steel and must be at least 8 feet in length. The diameter of the rod is also specified depending on the material. It is crucial to adhere to these requirements to ensure the ground rods can effectively handle fault current. If outdoor placement is feasible, it is recommended to locate the ground rods at least 6 feet away from the building foundation and any other structures. This spacing helps to minimize the potential for corrosion and ensures that the rods are in contact with undisturbed soil. The NEC also permits the use of other types of grounding electrodes, such as ground plates and concrete-encased electrodes, also known as UFA grounds. Ground plates are typically made of copper and are buried horizontally in the ground. UFA grounds consist of a steel reinforcing bar embedded in the concrete foundation of a building. These alternative grounding electrodes can be particularly effective in areas with high soil resistivity. When installing ground rods, it is important to drive them into the ground vertically. If obstructions are encountered, the rods can be angled at a maximum of 45 degrees from vertical. The top of the ground rod should be flush with or below ground level to prevent accidental tripping hazards. After installing the ground rods, it is essential to test the resistance to earth. This can be done using a ground resistance tester, which measures the resistance between the ground rods and the surrounding soil. If the resistance exceeds 25 ohms, an additional ground rod should be installed and connected in parallel with the existing rod. The NEC provides detailed guidelines for bonding grounding electrodes together. Bonding ensures that all grounding electrodes are at the same potential, minimizing the risk of voltage differences that could cause electrical shock. The bonding conductor must be sized appropriately based on the size of the service entrance conductors. In some cases, it may be necessary to use supplemental grounding electrodes to achieve a low resistance ground. Supplemental electrodes can include ground plates, concrete-encased electrodes, or even the metal underground water pipe. However, the water pipe must be supplemented by another type of electrode, as it cannot be the sole grounding electrode. When working with electrical systems, it is crucial to prioritize safety. Always de-energize circuits before working on them and use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you are not comfortable working with electricity, it is best to consult a qualified electrician. In summary, while indoor ground rod placement is permitted, outdoor placement is generally preferred due to better soil conditions. The NEC provides guidelines for grounding electrode systems, emphasizing the importance of achieving a low resistance ground. Factors such as soil type, rod depth, and proximity to other utilities should be considered when selecting a ground rod location. It is essential to adhere to NEC requirements for the size, material, and installation of ground rods. After installation, the resistance to earth should be tested to ensure effective grounding. Bonding all grounding electrodes together is crucial to minimize the risk of electrical shock. By following these best practices, you can ensure the safety and reliability of your electrical system.